Alright class, this is Ms. Riggins with today's video on comparing power, exponential, and log functions. And this is the last section in the chapter of chapter 11 that we'll be going over. Although I've done with you power functions, I know that before I came, you learned about exponential and logarithm functions. So if you don't remember enough about that, you might want to go back and review your notes or review those sections in the book regarding that. But first, let's take a look at the relationship between power functions and how power functions compare to one another. So let's suppose I have these two power functions, a x to the m and b x to the n, and they have positive coefficients, a and b. And to make things a little bit simpler, I'm going to rewrite the power of the f function into the n power from the other function plus some number k, where k is greater than 0. So basically I made it that f has the higher degree than g of x. So that means m is bigger than n. Okay? So the question is, when is this power function with the higher degree going to have function values that are larger than this power function? In other words, when is the difference of these two functions greater than 0? When is f of x minus g of x greater than 0? Well, when I do some algebraic manipulation, I see that since f of x is equal to ax to the m and b of x is equal to bx to the n, when I rewrite based off that difference thing that I included, it looks like this. And then I break apart the n and the k, and I get something like this. And then I basically divide both sides by a. So now this function has, this side is, well, this part has x to the n, x to the k, and this part now has b over a, x to the n. And then I factor out an x to the n, so I get x to the k minus b over a. Why is all of that? Well, this tells me when I have two cases to ensure that this side is greater than 0, i.e. f of x is bigger than g of x. And that is whenever x sub n is greater than 0, i.e. when x is greater than 0. And also x to the k minus b over a has to be greater than 0. So in other words, there's some x value, and when I raise it to the k power, whenever x to the k is bigger than b over a, or in other words, whenever x is greater than the kth root of b over a, then that means I'm going to have that f of x is bigger than g of x. Or in the case where x of n is not greater than 0, it is less than 0, which means x is less than 0, then that means by default x is going to be smaller than the kth root of b over a. So in other words, I have two situations when f of x is going to be bigger than g of x. That's when x is negative for all negative x, and over here when x is bigger than the kth root of b over a. So in other words, at some point the power function with a higher degree will be have function values that are greater than the power function with less degree. So if we go back to our notes, we can see that we have this statement that says something similar to it. Let me move it over so you can see. And that says that when comparing power functions with positive coefficients, blank powers eventually dominate or overtake. And if you said higher powers, you were actually correct. Higher powers should go here. And that's kind of intuitive because of power function, but it not only works for positive powers, but also works for any power, as we proved. And I've attached the proof to your notes, and you can see why. The second of four statements you're going to be hearing about, we're really not going to prove or not have time to prove, or the math that we know. We really don't know enough of the math yet to be able to show you the proof, but you're going to have to trust. And that's in comparison between exponential functions and power functions. And if you remember, exponential functions is, so if you remember, exponential functions are the form a to the x, and sometimes you may have a multiplier here. So the idea is that eventually any positive increasing exponential function is going to be greater than any power function. When you use the same variable. So I'm just going to say c times x to the n. Eventually. Now, it may not be initially, but it will be eventually. And we can see that if we plug in any power function into a calculator and compare it with an exponential function, eventually the power function is going to overpower the, the exponential function is going to overpower the power function. So in order to fill this in, any positive increasing exponential function eventually grows faster than any power function. And I can show you that using the TI Inspire, but we don't always have enough time for that. So, but if you want to know or you want to see that, we can do some examples in class. Just let me know. The third statement is about decreasing exponential functions in comparing to power functions, decreasing power functions. So in this case, if you remember, this is an exponential function, and it's only decreasing when when a is a number between 0 and 1. So if you remember, a has to be between 0 and 1. That's how you know it's going to be a decreasing exponential function, exponential function. Okay, and so what we want to look at is compare decreasing exponential function with a positive decreasing power function. In that case, that's something where it's c times x to the negative n, where negative n is less than 0. Okay? Not saying the function values are less than 0, because here, in order for it to be positive, c is greater than 0. But in order for it to be decreasing positive power function. So let's take a look at an Inspire file. And here we have two functions. If you want to take a look at it, one of the functions is 1/2 to the x, and that's the blue function. And as you can see, it's positive and decreasing. And the other function is x to the negative 2. And as you can see, it's also decreasing the blue function. Well, if we take a look at the t values, table values, we can see that as x, let me move this so you can see, that which one is approaching the horizontal, they both have horizontal asymptotes of y equals 0, but which one is approaching there quickly? Well, as you can see, at first it's the blue one, which is the power function, and then they seem to be pretty much equal, and then you seem to see that it's the red function, which is getting closer to the horizontal asymptote quicker. And as we can see, then it sometimes looks like they're at the same value, and then we can see now that they're very neck and neck. Like this one is closer, and then we can see that now this one is closer. And as we keep going, we notice that now it seems like the exponential function is approaching it quicker than the other value. So that lets us know that eventually the exponential power function will approach the horizontal asymptote quicker than the power function. So we go back to our notes, and that means that we can include here and say any positive decreasing exponential function eventually approaches the horizontal axis faster than any positive decreasing power function, and eventually is the key phrase right there. Okay, and then we have, that's our third statement, and you can still use the same information to prove the previous statement for increasing positive power functions, but in the interest of time I didn't prove that, or I didn't show that. And then the last statement is regarding power functions and log functions, and that's a little bit more different because we haven't seen log functions as well. And so in this case, any positive increasing power function eventually grows more rapidly than a log function. If you remember, a log function looks something like this, log to the power, log to the base of x. And we may have some multiplier. Who cares? And it says, unfortunately, the log function grows slowly. If you remember, well, I wasn't there to teach you logarithms, but logs grow very slowly compared to basically any of our more popular graphs. So I would show it to you in proofs, but in this case we really don't have time. But trust me, any positive increasing power function will grow more rapidly than any log function eventually. So those are the notes. I hope oops, and I guess I'll talk to you tomorrow. All right. See if I can figure out how to end this. Hmm.